Let me go to an associated topic, what is called line detection. Now let us talk about line detection. So until now, right, we know that we have got these right edge pixels if you use a canny or something, and of course it is not really deep network. I am again kind of switching back to a traditional thing. So the thing is, right, I mean, okay, so for example, right, you could have an image, right, now where let's say, right, you have these, right, these is your edge pixels, and you know what, you would think that all of these probably fall on a line, right, and therefore you know the output should perhaps be more or less a line, right, which I should be able to pass through. I mean, which in a sense, right, which I kind of believe that you know that these points kind of lie on a line, and therefore, right, I mean, so for example, if I see an image, right, if I see a wall here, right, if I see a wall there, then instead of seeing them as edge pixels, I would want to kind of draw a line through them, draw a line through them, draw a line through them automatically, right, and because a line, right, you know, would give you a lot more information than simply having those say edge, no, this one, the pixels. The other thing is that edge pixels need not be restricted to lines. For example, you know, you could have these edge pixels sitting on some kind of an ellipse or something, or they could be sitting on some circle or something. To us immediately, right, it may not be, you know, to the algorithm it's still an edge pixel sitting in isolation, but then when they are brought together, right, they could actually give out a much more meaningful information. For example, if I gave you a human face, somebody in an image against a background, and I asked you to pick out the human face, what will be the simplest thing that you would do? What would be the simplest thing you would do? What will be your simplest idea? Ellipse, exactly, right. So you would say that, you know, get me an ellipse, whichever object looks like it, because the face is somewhat ellipse, right, elliptical. So instead of looking at facial features and worrying about all that, I will say, right, pick all those objects that can be fit into and say, right, elliptical equation, right. I mean, something like that you can do. So that's a kind of a quick entry into to seeing where the faces are, rather than saying, you know, construct something for a face and all that. So I'm just saying, so where they can be applied, how they can be applied, right, is all right. I mean, so I think it's all up to us. So the idea is that right, you might want to. So in this case, right, I mean, you know, I'm just taking line as an example, because that's the simplest which you can ask. So there is something called a Hough transform. Okay, it goes off after a person, okay, whose name is I think some C.V. Hough or something. Okay, so it's called the Hough transform, and the Hough transform's goal is this, right, and you can have a Hough transform for line detection. You also have a Hough transform for circle detection, ellipse detection. We don't want to go into all of that. I just want to give one example so that you understand the basic philosophy. Right, so this is kind of a voting method. Okay, this Hough transform is something like a kind of a voting method, and Hough transform for line detection. Okay, so we are looking at line detection. So it starts with this simple idea that for example, right, I mean, if I have, let me say, right, I mean, I have a line here. Okay. Now, one way to, of course, one of the things that this Hough transform needs is that there should be an equation, right, a parametric equation for, let's say, whatever object you are actually looking for. Okay, so it's like saying that, so suppose I have the slope-intercept form. What is that? I mean, y is equal to mx plus c, right? This is a kind of a slope-intercept form, right? Now, what I can actually tell is, if I actually know the so for example, I mean, if I know say m and c, right, then if I kind of walk along x, right, if I walk along x, then I can find out all those y's, right, which actually sit on this line, correct. So I can say which are all the points that actually satisfy this equation of the line. So all that I need to know is the m and c, right, and then for that, as I keep varying my x, I can find out what are all the y's that actually satisfy this equation. Now the right interesting thing, right, about this is that I mean, right, just to kind of right, what do you say, give you an intuition, is that when you see in an image, right, what you do, you don't see the line directly, right, the canny or something doesn't understand line. So what you see is points. So you see a point there, you see a point there, right, something in the most ideal case, right, they're all, of course, you may not see all of them, right, you might have actually thresholded something would have vanished, maybe after this you get a point there, but there is still some point there. Okay, now the point is, right, for through each point, right, I mean, if I just take this point, right, then I can think of infinite lines, right, which can actually pass through that point, right. So which means that there are so many MNCs, right? I mean, so you can think of so many lines which actually pass through that. But there is something which is actually common to these points in the sense that each one of them, right? So for example, each one of them certainly has this one, and one is MNC, which is this line, right, which I have drawn. The point is how do you actually tap that information, right? So how do you tap the information that these fellows are all actually falling on a line? So one way to kind of, right, do it is you actually create a discretized space, simply like where you can have a grid where you have M and C values, and then start to see, and then, right, I mean start to kind of, right, I mean fill that grid in a particular way. I won't kind of go into that because something more something else is actually done, because this has one problem. Right, this slope-intercept form has one problem. What is that problem? So if you were to think about if you had to think about some kind of a voting scheme, right, where you want to see, I mean, how many of these points vote for one particular MNC. Okay, I mean, if you had to do that, then that will sort of give you an indication that there are enough number of points voting for one MNC, and therefore probably there is a line that's passing through that. But then there is a problem with that. What is the problem? The problem is mainly in terms of a line, right? For example, if you have, let's say, y equal to a constant. Right. So for example, if you had, when what do you say? So sorry, I mean, right, I mean, if you had, let's say, x equal to what is this? So if you have an equation like this, right? So that's like what, x equal to phi, right? That would be right, equation of this line, right? Now an equation, so a line like this will have actually infinite slope, right? So this m can right, typically can be right unbounded. I mean, if I start, right, making this line, right, vertical and vertical and vertical, there will, because you will have lines like that also. No, you can't say that no vertical lines don't even exist in my image. You can't say that. In fact, many a time when you look at a wall, there are so many vertical lines, and therefore you have to be able to, right, deal with them. Therefore, this slope-intercept form is not the one that, let's say, people use. One of the main reasons is because the slope can become unbounded, and this guy cannot handle it. What is the alternate form for a line that you are familiar with? I think, I'm sure, I mean, that you must all, I mean, in your 11, 12 somewhere you would have done it, no? What is called a normal form, right? What is the, so you have something called a normal form of a line. What is that normal form? What is the normal form of a line? Anybody? Exactly, right. So for this line, right, so from the origin, right, I mean, you find out a point on the line, which is closest to the origin, which is of course, which is actually the line which is orthogonal to that line, which is a perpendicular. Oops, wait a minute. Yeah, which is actually a perpendicular, and this you call as some length rho, and this you call as an angle theta, right. So with respect to the x-axis. Okay, then what you can do is you can actually write down the normal form, which I am not going to show and all. This is all very straightforward, right. You can, this is all just 10th, 11th or whatever. So rho is equal to, I think, what is it? I mean, x cos theta plus y sin theta. Okay, this is called a normal form of a line. Okay, this is what the Hough transform uses, not the slope-intercept form. Why? Because, right, I mean, in this, okay, I mean, instead of M and C, rho and this angle theta actually play a role. Okay, but in the, right, nice thing is, see, for example, I mean, right, I mean, if I wanted x equal to phi, which here, right, in order to express x equal to phi, I need an infinite slope. Whereas right, if I wanted x equal to phi, what would I do here? What will be my this one theta, and what will be my rho? Rho will phi, and then theta will be 0, right. So it means that we just finite. So wherever I go, right, whichever line I want, I can always say represent, even if I want x equal to 0, right, I mean, so if I want to represent the y axis, which is what, x equal to 0, right, okay, and if I want the x axis, that will be like y equal to 0, whatever it is, any line on this plane, it can be expressed with just finite values of rho and theta. They never go unbounded. Okay, so that's why a normal form makes actually a lot more sense. And the same thing applies. See, for example, if I fix a rho and actually a theta, right, that means right, this rho, okay, which I have fixed, and then I have this kind of say theta, and then if I vary my x, then all those points, right, that lie on this line are the ones whose y will satisfy this equation. Correct. Now the main thing, right, which this allows you to do it is now similarly you can go for some kind of a voting. But now the advantage is that you don't have to worry about unbounded values and so on. Of course, there are some, there is a slight variation in the way, let's say, right, people do it. So usually the standard form is to let theta go from 0 to pi. Okay, that means you go all the way from say 0 to pi, and then let rho can be both positive as well as say negative. I mean, you could have had theta going from 0 to 2 pi, in which case rho right, could have been simply a positive number, but the more standard thing to do is actually to let theta go from 0 to pi, and then so for example, so your rho, if it is on this side, then we will take actually a negative sign for that. Okay. So this rho is like this. I mean, this is just one a construction aspect. But right, what is more more interesting is this. See, suppose for example, right, I have this grid. Okay, let us say that right, on this, along this axis I have my rho values, and along this axis I have the theta values. Let us say I simply put the rho as 1 and then 0 minus. What will be the range of rho, by the way? Yeah, if I have an n cross n image, what can be the maximum rho that I can go to? M by root 2. I mean m by 2, no? M by root 2. Right? So you can go like so. So here I have just put it as 1 and minus 1. Typically it will be like m by root 2 to actually minus m by root 2. Okay, that will be the range of rho if I have an m cross m image, right? Because you have this image, and then if you want to find out which is the farthest diagonal, which is the longest diagonal, right? Okay, which you can have, then you have like m by 2 and root whatever, right? And that will give you m by root 2. Therefore, this rho in general can go from m by root 2 to minus m by root 2, and then theta will go from 0 to pi. Okay. Now, if I take a point, okay, see, I think so the way to kind of look at this is, it's actually interesting. It's like actually a sort of a duality. Here, I mean, right, duality is in terms of what you fix. See, for example, right, I mean, so for example, right, in this case, suppose I say that, okay, let me just go back to the equation. Rho is equal to x cos theta plus say y sin theta, right. Now, if I take a point, right, so let us kind of go back to that image that I had, right, so suppose I take some x, of course, one of the things is, okay, let's leave it. So if I take a point x comma y, okay, I take a point x comma y, because that's what I have on my image, right, I have so many x comma y's there. So I take one x comma y, right, from that. So I have my image, right, wherein I have done a canny edge detector or something. I have lots of these guys, right, these pixels. Some of them, of course, seem to lie along a line. So I am taking one such pixel, which has some x comma y, right, which is this x comma y, right, which I am. So let's think about this line as this line, right. Now when I kind of say take this x comma y, and if I change my angle theta, so that means my x and y are frozen here, right. I have taken an x and y. If I change my angle theta, what kind of a curve what kind of a thing will I see here? What will I plot? What will I end up plotting? I have to plot rho, no? I am varying theta. I have x and y fixed. That means what? Rho will change. What law will it follow? It will follow a sinusoidal law, right? Because it's kind of cos theta plus y sin theta, right? So what will happen is, right? So I mean, I don't have the exact figure, but something like this is what you will get for that one point. And so that one point traces a sinusoidal curve, a cosine or whatever, right? I mean, a curve on the. So this is called the Hough space. This is called the Hough space, or the say theta rho theta space. Okay, which is of course a discretized space. By the way, there is there's a lot of studies on how best to quantize and so on. Let's not. The idea is not to enter into all that. Okay, but the idea is that you have a Hough space, right, and in which this guy traces a curve. Now suppose I took one more point, right. So it's like another point on this edge. I don't know whether it is there on that edge, but I've just taken one more point, which is another xy. Now I plot this. What will happen? That will also be a sinusoidal curve, right, because I'm going to fix another x comma y, and I'm going to vary my theta from 0 to pi. I'll plot my rho. What will happen? Yeah, exactly, right. So what will happen is, so the other guy, right, might actually come like this and then go off like that, but then they will actually intersect here, because that because of the fact that they both lie on one line with a rho and actually a theta, right. So among all the rhos and thetas that they can span, there will be one rho and theta which they both will actually vote for. That's why this voting comes. So for example, so if I take another point, right, it might be like that, right, it might go like that, but that will also cross that point and go, because of the fact that they are all lying on the same line. So if you now do this, what will happen is, right, I mean, if you actually accumulate, right, so if you accumulate these votes that you are getting, now if something is lying on a line, right, then all of them will try to vote for, let's say, one bin, right. If you think about this as a discretized space, okay, so actually ideally what you have is actually this one, a discretized kind of space, okay. I mean, you can actually do a discretization, whatever. I mean, there are various strategies for that. That's not the intent of this lecture. Okay, so then the idea is that, okay, this guy, right, will get flagged as a very high number, and you can imagine, right, in an image, if I tell you that I have a line, then you can imagine how many of these points lie on that, right, if there is a line actually. So then kind of, right, what will happen is then that, so when you kind of, right, eventually look at sort of a local maximum, okay, then right, you may have one here, and then right, I mean, you might have, so it's not true that you will have just one line, right, in an image, no, but these guys will actually stand out. You may also have, what else can happen? Are these the only two things you will see? I mean, like, let's say I have two lines, okay, in that line, okay, there I'll say two lines, huh? Now what will my Hough space look like? Will these, so let's say for the other line there is some other rho theta, right, that gets flagged, okay, that's also a very significantly high number. This is also a significantly high number, and I know that, okay, that there are actually two lines now, okay, in this image. Anything else? I mean, will it be as clean as this space, this Hough space? What else can happen? Huh? Exactly, right. So basically what will also happen is, I mean, you have got these two lines, but then there are also points going, I mean, you can also think of lines going through, let's say, 2 points, right. 2 points, I mean, you can always draw a line, no. So you will also have some little votes here and there, but those have to be ignored, right, because those are not really, when you say that you have a line, it doesn't mean, right, 2 points. I mean, that's the way we might, but that's not the way this interprets it. It says there should be a dominant line in the image with lots of H pixels supporting it. Okay, that's why this, you have this voting this mechanism. Otherwise, you will end up drawing so many lines, right, I mean, through that image which won't even make sense. So when we say this, we actually, we understand that it's not like, right, these are the only two things that are going to get flagged, but these are the, if there are two lines, then those two will get predominantly high number of votes, right, and which will stand out, and you will know that, okay, these are the lines, okay. So right, let me just write this down just for the benefit of because these things sometimes, right, I mean, you'll have to search all over the place.
So only after flagging the H pixels we are doing.
Yeah, only after we have actually we have flagged the edge. So that's like the output of a canny edge detector we have now, and we want to tell what are all the lines through this image now. I think I started by saying that. Yeah. So the Hough transform, right? So the way to kind of think about the Hough transform is like this. So first is create a 2D quantized r theta space, so rho theta space. Then what you do is, next is for each edge point, so it's already there, okay, it has to be an edge point. Let's say xi comma yj, all the histogram bins, okay, I mean the histogram, you know, right, what is histogram? The histogram bins in rho theta space that correspond to the HT, Hough transform, that is the sinusoidal curve, for a point, for each point, all the, wait a minute, for each h point, oh, increment, okay, oh, yeah, I think that's what I was thinking. For each h point, xi comma increment, okay, there should be a word increment here, and that's missing. Increment all the histogram bins in rho theta space that actually correspond to the sinusoidal curve for a point at that location. So, what this means is, and that is a location. So, it's like, each of, so when you say histogram bins, what you are trying to say is how many votes, right, each let's say one of those bins that you have in that Hough space, right, how much of votes, right, is it able to get. So, when you take an xi comma yj, then you find that sinusoidal law, and then you go and increment each one of those bins wherever it falls. Then repeat the above step, let us say call this step 1, repeat step 1 for all these h points. For all the h points, and to find the line segments, what you will do is search the rho versus theta histogram for a local maxima, or for a local maxima or peaks, because it does not have to be just one, right. So, maxima, peaks, then generate lines corresponding to the rho theta coordinates. Of the local maxima. That means for all those rho theta bins for which you have maximum value, or those which have turned out to be peaks, generate lines corresponding to them. So, what does it mean to generate lines? Simply join all those points to the rho theta coordinates of the local maxima. Okay, yeah, that's it. And then I think there is some pictures, right, that I wanted to show you. So, where is that? So, you go and see this, right. Anyway, okay, these are again from the past one. Okay. Huh?
The histogram, when you arrange it in descending order and choose which lines, the threshold will be like the base
Threshold will, yeah. So, what you normally do is, so for example, you look at, you do this non-maxima kind of a suppression. So, on that grid, right, wherever you are sitting, if you have a local maxima, then you will also look around. Okay, it may happen that, right, depending upon how these points are, right, it may happen that you may also have something else which is also not so low. Then you just, because you do not expect two lines to be that close, right, what you will do is you will suppress one. Again, that is like, you could actually be wrong by doing that, but then you just look at the numbers.
Maybe the point of intersection is actually
between those two, because again, right, this is actually a discretized space, right. So, quantized space. So, some approximations have to happen. It is not like it is an entirely clean thing, but see, the idea is that it's a very kind of neat way to actually do it, right. Everything will have, nothing is like 100% this one, but yeah, more or less, right, it will actually work well. I will show you some examples, right. So, for example, right, if you had an image like this, right, then and a thresholding, assume that we have performed some edge detection, right, and so for example, right, so here is where you have those edge pixels. You still do not know which of them are lines, but of course, to your visual eye, right, you can immediately see that these are those predominant lines and so on. But then after you pass it through a Hough transform, right, then you see that that actually picks up the ones that are the most significant, right. And again, right, depending upon your application, you may want to go back and retweak and then allow a few more and so on. But then the idea is that right, in that Hough space there is still so much information out there. For example, right, it might look like something like this. So, it is not like entirely clean. It is not like this is a one peak or something. So, for example, right here, this spanner. So, if you see, right, so if you see after kind of detecting the lines, right, it's passing a line straight through. Right, those two are your lines, okay, which are your output, and even if you have noise and all, it can still do it. That's what is actually nice about it. Which is why, anyway, I will tell you some other day. So here it says these top 20 most voted lines. Okay, so you can say, can I have these top 40, and then maybe there if you see that too many unnecessary lines are coming, then maybe you will just stop it. That's a hyperparameter then. You have to stop, right? You have to do a thresholding somewhere. No, say that only these are significant. Advantages: conceptually simple, easy to implement, handles missing and occluded data. What does that mean? A discontinuity, yeah. So something is obstructing something. For example, right, I have a line, but then suppose I place an object, on top of it. Now I can't see these at all. No, these pixels I don't see. Something else has come and sat on it. But then a Hough transform allows me to draw that line through the occlusion, because it knows that these are all supposed to be on a line. Therefore, something should have been underneath which has been occluded, or which is kind of partially visible, or whatever. Right? So it can actually handle that gracefully. And then can be adapted to many types of forms. So now you can think, right, if I had circles, then maybe, right, you can have a Hough space for circles, you can have Hough space for ellipse, which is all there, by the way. Then the disadvantage is that, yeah, the more complex the object becomes, there is then this kind of a parametric form, right, can be more and more involved. I mean, this was a line, so maybe my idea in talking about this line was to simply convey what is underlying, what is a principle of the Hough transform. But where all it can be applied, you can always, right, escalate it and then go to other objects. And looks for only one single type of object, in the sense that there's only lines which you are looking for, right, at a time. And then the length and the where the line exists. I mean, not that. I mean, so I mean, you can't tell what is the kind of length of the line, right, because it will just draw a line all through. That's it. And then collinear segments, right, it cannot actually separate, right, because it will think that the whole thing is a line. See, for example, right, I mean, if you had a line like this, in between, if you did not have anything, it might still believe that, right, that there was a line through it. Now you will have to take a call on whether I should treat this in between as empty, that there was nothing there, or whether I want to consider that something was there. Just that my edge pixels, when I did a canny, right, those things got lost. And those are all weak pixels, they probably went away, but then they ideally should exist there, and therefore, right, I will actually allow this line to run through. But this cannot tell on its own, it just draws a line through and through. Okay, so we will stop here for today and then meet whatever next week.